So with the shell model in hand, we can say some things about the total nuclear spin, total and its parity, and its magnetic moment. Now, with the completed shells, we expect, like in atomic physics, that a complete shell will have total angular momentum 0. In fact, it must have, because we've included all the angular momentum states possible. And so that doubly magic numbered nuclei should have no spin, and in fact that is found. So the alpha particle has spin 0, the oxygen 16 nucleus has spin 0, for the 2020 and the 2028 nuclei have spin 0, and likewise. It turns out, however, that for even A nuclei with even Z and even N, those also have no spin observed. All nuclei with even numbers of protons and even number of neutrons have no spin, so that in fact the protons and the neutrons both always pair in their spin with each other. And it's only unpaired spins that determine the properties. So that if A is odd, there is either one unpaired neutron or one unpaired proton, which determines the spin of the total nucleus, and one can calculate what that is. So for instance, for 25 magnesium, we discussed last time, the protons have a filled shells, and then 1d 5/2 to the 4th for protons, 1d 5/2 to the 5 for neutrons. So there's one unpaired neutron in the 1d 5/2 state, so that we expect the total spin, in this case, to be 5/2. So that 25 magnesium has a spin of 5/2. We can do this with reasonable accuracy for all odd A nuclei and get reasonable values for the total nuclear spin. For the A even, Z odd, N odd states, it's more complicated because there are two unpaired. There's an unpaired proton and an unpaired neutron, and we don't know exactly how to combine their two spins into one because they're not paired. Now, we can also do the same thing and talk about the parity. Now, the parity only in the nuclear state only comes from the orbital angular momentum. And it turns out that the parity of an angular momentum state, L, depends on whether L is even or L is odd. So if L is even, the parity is even or plus. If L is odd, the parity is odd or minus. And we could see that, for instance, in the solutions for the one-dimensional harmonic oscillator. Well, that's not a good example. For the three-dimensional oscillator with n equals 1 and L equals 0, we had a wave function that looked like this. And you can imagine wrapping that around in any direction, and when you flip that over, change all the directions to their opposite directions, you get the same function back. It's however, when we had L equals 1, we had a state that looked like this. And if you imagine flipping that over, it's going to look on the other side something like this. And as you change from positive to negative, you get a minus sign. In fact, the parity comes with the spherical harmonics in this case, but the same argument applies. Only with L equals odd do you have 1/2 of your sphere positive, and if you go to the antipodal part of the sphere, it'll be negative if L is odd. And so going back to our 25 magnesium state, we knew that it was in a 1 d5 halves, the lone neutron unpaired there. So d goes to L equals 2. L equals 2 is even. So in fact, the 25 magnesium has a spin parity of, which we often write J pi, like this, equals 5 halves positive. Again, for the even odd nuclei, we can determine this directly. We can also say a little bit about the nuclear magnetic moment based on the shell model, but we can also say that sometimes it works and sometimes it does not. It certainly does work for even n, even z nuclei, even nuclei, which are predicted to have no magnetic moment, no spin, and indeed they have therefore no magnetic moment. And for some of the even odd cases we can do as well, but it's for the odd cases that perhaps we can work best. So for instance, for the deuteron, we have 2H. It has one unpaired proton and one unpaired neutron, obviously. And if one assumes that they are, so we know experimentally that it's a spin 1 case, so the proton and neutron spins are aligned, which means their angular momentum state must be 0. This is important because the proton does not have any angular momentum in this state. So therefore, the deuteron's magnetic moment, we might expect, is just going to be the sum of the two, the proton and neutron magnetic moments. So we would take 2.79 times the nuclear magneton for the proton and add the 1.91 minus 1.91 nuclear magneton for the neutron to get a value of 0.88 nuclear magnetons for the deuteron, and that is close to the measured value of 0.86. We can also do another case for boron 10. Boron has 5 protons, so this is 5 protons and 5 neutrons. So this is, 1 p 3 halves, 1 p 3 halves, 3 of each of these. So one unpaired p 3 halves state. P means L equals 1, and so there's one unpaired proton in an L equals 1 state. So in this case, we expect to have a magnetic moment that would be 2.79 from the unpaired proton, but plus 1 nuclear magneton from its angular momentum, and then minus 1.91 nuclear magneton for the unpaired neutron's spin, which gives 1.88 nuclear magneton, in good agreement with the 1.80 measurement. However, this doesn't work as well in many other cases, and one can set a range where the nuclear magnetons can be, and they fill out much of that area.